Good morning, everyone. My name is Tom Hengl. I'm the founder of OpenGeoHub and also technical director. And welcome to the Open Data Science Europe workshop. It's a one-week event with the first 2 days, as you know, training sessions. Training sessions are split into 2 parallel sessions. I hope you managed to find the right session. This one is on R. The one above us, it's on the Python. So we have 2 training sessions, and we'll do two days training, and then Wednesday, Thursday to Friday, it's a conference with a conference program with live talks. But you will see also that it's also going to be quite similar topics, so things that we'll be doing the training. You will see that in presentations they will come. They will just be on a high level. So the program we will follow, the one you find online on the opendatascience.eu. Let me share my slides. And as you see, let me share my screen first, actually. As you see from the program, we are using this virtual box. So I'll be using this virtual box. Don't get confused. I can switch in my Windows 10 system. I can switch to Ubuntu. So I just press a button, and now I'm on Ubuntu. And if I do Control F, then looks like I'm on Ubuntu computer, but it's running on my local machine. It's really magical. So we will be doing this virtual box. Why we do virtual box? Because we want that you can all access exactly the same, and we don't lose any time on installing, downloading, setting up. Also have in mind that these slides you can make available offline. So if you, I shared all the slides, right? You can find them on in the MetaMost channel. So I shared all the slides, and you can access the slides. And if you want to save bandwidth, then just go and make them available offline. So that will be something like here. So these ones we are starting. So I would just go File, Make Available Offline. And this way you save bandwidth, because if you don't make it, then switching between a slide can cause bandwidth conjunction. So that's why you should try to do it, save things on offline. So I can start with this first block. The blocks are 1.5 hours. We will leave every block, we will leave about 15 minutes, which we will stop doing YouTube broadcast, and then we focus more on your questions. But in the meantime, we will answer questions from people that are online. We will have every day, I think we will have maybe 50 to 100 people following online, depending on the block. And some people in different time zones, so probably the way to connect later on. Let me start the presentation here. No, I can just use like this, I think. So we have today and tomorrow. I will be the teacher. I'll have some help from Carmelo. He's not with us now, but Carmelo will help with the spatial temporal ensemble machine learning, especially because he's working with the real data. So that's the one in the afternoon, and then also we will do one more technical session working with cloud optimized geotiffs. It's something maybe new to many of you, so we will do quite gentle steps. We will guide you step by step how you use a cloud optimized geotiff, and again, especially with the intent to show you how to do it in R. And the guys upstairs, they will do practically similar sessions, but more focus on Python. Python and R, of course, are not one-to-one. There's many functionality that is really different in Python and from R, and there's many packages that exist only in R. And there's many packages that in functionality exists only in Python, and some things computationally it's more suited for Python. And some things for like plotting and statistics is more suited for R. So when people ask, okay, which one should I learn? Usual question. My answer is both. It's very simple. And you can, we can maybe show that, but in RStudio today you have also functionality to connect to, so if I go to RStudio, there is a functionality also to connect to Reticulate. To connect to the using, so here if I go think under, let me see, it's under tools, I think. So you can connect to the vReticular to Python, and then you can do Python programming also. So that's about Python and R. Going back, so this morning, first block, it's a, let's say, gentle introduction to spatiotemporal data, specific of the data. You know, some things may be aware of, some things maybe here for the first time. I'm hoping most of things you will hear in this block for the first time. And then after that, after the break, we'll do some modeling exercises, and then slowly I will start jumping from R to Python. Sorry, from R to slides. So you can see me actually doing programming and working with real data. And then this morning, basically, it's a kind of warm up for the real session, which is the spatiotemporal ensemble machine learning. And that's something I think possibly new for you, and this is going to be really hands-on. But then we just explain you how it's done. And some people tell me, oh, you know, you think like it's simple, but actually this ensemble machine learning is highly, if you do it for the first time, it's there's a lot of components, and it's really highly complex. So it requires like really, I think, gentle introduction and that you feel the data and the code. Everything I will do, it's basically in this notebook. So there's this notebook, so it's here. And you see this notebook is under R training. And I did share it with you already last week. I don't know if you managed to look at it, but this one, it has all the examples and even has text, so you can really follow it. It's really like a computational notebook. So you can really follow it, and at the beginning there's a bit of introduction, but then very quickly you have functions, and you run the functions, and then you can let's say you can test your own thing. So we will be moving through this tutorial just here in our studio, and we will be looking at different things. And so you see, I can move through some section. I can run a function, source the function, and then I can. I get some warning message, I don't know, but I can compute something and get a number. So that's this computational notebook, and that's what the guys use in Python upstairs, this Jupyter, whatever. So it's basically looks the same, and we can scroll through the different sections, and then we will test things, and then you can modify that code, by the way. VR Studio, you can modify it, you can play with it, it's no problem. If you do something wrong, there is a shortcut. Let me see. So you can do git stash, and this will remove all the changes. So it's very nice to know the git command. So I can just do git stash. If I go here, sorry. Let's see. So if I do this, I have to get to the folder though first. So that's somewhere under. Let me see, where am I? I need to remind myself. So that's under the home ODSE work directory. Home ODSE work directory. ODSE. Then ODSE work directory, and then code, and then ODSE workshop. So first I change here, and then I can do this git stash, and this git stash will basically remove all the changes. It will leave all the new files you make, but if you mess up something, I don't know what I did, and then you just do git stash, and that will revert it into the original. Okay. So you see, I have this cheat sheet. I can share this with you, but more or less it's just a basic survival. If something happens, we have to restart the Docker. So that's also a survival tip. But I can share that with you. So that's the plan for these days. Is we use this tutorial and then we will go step by step through different steps, and then you can ask questions, and we can slow down, and we can zoom in into things. Also, I shared, as I said, I shared the slides with you. So you don't have to write anything down. You don't have to make screenshots. Remember, this is also video recorded. Everything I say, I do the code. You can follow after the course. So you can really be relaxed and just really focus on the course and ask questions and see if you can reproduce something on your laptop. Why we like that people use laptops? It's well, it's less maintenance for us, and obviously you can use different operating systems. But also we want that you learn how to use software. So as soon as you go back to your office and to your work, that you can continue using the software. Also, why we want that you use laptops is you can interact with us, you can ask questions, and Mattermost is very important because you can do a screenshot if you have a problem and say, I have a bug, something's happening, then you can send a screenshot and then we can try to help you. And as you can see, there were many people asking questions about the VirtualBox, and there was screenshots, people saying, I have this problem, I have this problem. So people were sending, so we were debugging already and helping people. And I hope now you all have that VirtualBox running. By the way, I'm also new to VirtualBox. I didn't use it before. You would just connect to my workstation at office using a no machine or TeamViewer. But now Leandro convinced me it is the best way. It's very elegant, and you just, it's kind of, that's why it's called box. So you have everything out of box. You have all the software, everything is customized. We all see the same, and you can easily just turn it off. And you can put it in standby. I don't know if you tested it. You put it in standby, and then when you start the machine, you get exactly the same thing where you left. So it's really magical. Okay, so that's the Mattermost. Anybody not connected or the art development group, please connect. If you don't see the art development group, you have to go to this plus sign, and you have to say browse channels, and then pick up the channels you want to see. If you are a physical participant, if you have questions about logistics here at the WIC, then you should ask it in this group. Don't mix it. If it's a general question about methods, problems with code, then you ask in the town square or you ask in art dev. But if you have a question specifically, I have problem with Wi-Fi, I have, then you ask it here. So that's and it's very important to use Mattermost because it keeps a track of everything, and you can open lots of discussion groups. And everything you post basically becomes a little discussion group. And if you reply on something, as you see here, when you reply, you can see all the thread. So that's also nice about the Mattermost now, that you can go back to the same issue raised and then you can respond there. And usually if we responded to something that you asked, we will not respond back, but we are going to just send you the link, and you can link to any thread or any post in Mattermost. It's kind of like in GitLab, and so you can link to any post. And this way we can debug, but we cannot. If we debug a problem once, we don't want to debug it 2 times. I hope you understand that, because that's a waste of time. Okay, everybody looks very serious. There's no exam, by the way, in this course, so you can relax. This is, and it's also special times. This is Corona pandemic times, and we are really doing our best and improvising. We had to teach ourselves how to do parallel broadcast and, you know, how to use all the Zoom functionality. We haven't used it before. And also there were many cancellations, by the way, for physical attendance. 25 people canceled, so really high cancellation rate. But we had the last year, exactly here at WIC, we had a summer school, and there were more people, almost 2 times more people last year when there was no vaccinations and more chaos. And now that you would think, okay, there's vaccinations, but the Delta unfortunately arrived, and that made it a bit complicated. But nevertheless, we'll keep it in. We'll keep everybody safe, of course, and So we will do our best to follow the Corona rules, of course, and we think it's going to be a successful event. Nevertheless, if you're new to R, it's not. I cannot promise you're going to leave this place and you say, I went to this training course 2 days and I learned ensemble machine learning in R. I never used R before. That will be very difficult. This is quite advanced topic. You know, there are ways to teach somebody in 1 day things with the right motivation. I mean, imagine this person here, you know, trying to satisfy Kim Jong-un, and if he fails something, of course, it's not a good problem for him. But there's very difficult to teach something very advanced in 1 day. So what I recommend is that you kind of, if you are new to many things, open your mind and just make sure you you know, take the copies of the slides, and remember there's going to be a video published also, so you can go back to some of the discussion points and you can see me coding, and you can teach yourself after the course. You can go back and try to learn things. The reason why we're here, of course, is because we have a European funded project, which is called, actually, project called GeoHarmonizer, but that's a too technical name, so we renamed it to Open Data Science EU. And so that's the reason why we have this, because we had some budget to organize this type of workshops and to do co-development sessions. So this falls under one of the co-development sessions, because we also expect to get feedback from you. But so this is our project, and you can read on the bottom, you see that it's been funded. It used to be called INEA, Innovation Networking Agency. Now it's called HADEA. But you can read about this project here under the link, and it's mentioned on the bottom of the page. I can see there's some people now connected from US, which is really crazy, because I think it's probably like 4 a.m. or something. But I see lots of people connected now following around Europe, and there's some people following, looks like, from India. So you can read more about the project, and we post here, if we have the news, then we post some articles how we did processing, but they're very short. So we are hoping, we're writing now articles to explain how we did the processing. So that's thanks to this. And as you see in that project, we made this data portal, which is under Maps, Open Data Science. So if I actually have it here, I can go. So under the Maps Open Data Science.eu, we made this what we call a European Environmental Data Cube. And this is the Data Cube viewer. So we made this data portal, and as you see, we are here in Netherlands, and we can zoom in. So let's say we are now here, Wageningen. And so what we did, we created this land cover predictions using ensemble machine learning. So the things we're teaching you, this is what we did, but we did it with 7 million points and with about 400 covariates. So the regression classification matrix is only classification matrix about 3 GB. And so we computed all these things. And we also put, we can show you, we put the points here. And so we trained with 7 million points, and we made the predictions, and you can go and scroll through time, and you can see how the land cover changes. And what you can see here is that this, for example, Veenendaal, like this area, you can see that there's a growth. So all these places are new. And we did the proper, I think, land cover mapping, because we mapped every class. So if you look at urban, we mapped every class as a probability. So you can see also probability of each class mapped. And so if I click somewhere here, I will get, it will do a query on the GeoTIFFs, and it will get the values of that probability changing through time. So we can see in which time they started building our estimate. Yes. And also, when I say we do things properly, we also put the uncertainty. So if I turn this off, we put also the uncertainty, and you can see uncertainty per pixel. We estimate which of the pixels, if it's a brighter yellow, it means there's a higher uncertainty, and it will pop up some places. You will see a higher uncertainty and it means that you should be careful using that data. So I think it's let's say a proper framework to do land cover mapping, and we are proud that we did it using ensemble machine learning. In this case, these predictions and the modeling was done in Python actually, but we also have the vegetation maps that Carmelo and me are going to show. This was all done in R. So once you choose R or Python, it's not easy to mix, but some projects we chose to use R, or some projects we chose to use Python. So yeah, that's this project, and that's what we're going to talk about. And we're very excited that Carmelo, who is a PhD student at OpenGeoHub and Wageningen University, he's going to show you in the afternoon, really with a really large data set. We're going to show you how we compute space-time distribution of forestry species. And we will show you that it really matches the ground data. We also have about 1 million point, I think, training points. So we are very excited to show you that results. This is also first time we're showing to public these results. Okay, space-time data. So I personally work a lot with spatial data, and I did a lot of predictive mapping projects. And I even produced some global data sets, European data sets, Africa, United States. I even won some awards for some publications on doing predictive mapping. But I also got interested already in year 2012. I knew that it would be very interesting to do space-time. And then I published my first paper, I think, on space-time in 2012, space-time prediction. And so we will use that paper. It's one of the case studies is the mapping the daily temperatures. And then later on, somewhere in 2018, 2019, I wanted to switch from doing spatial to space-time. And this project is a proof of concept that you could do all the mapping projects, you can switch to space-time as long as you have enough data. So when you look at the land cover mapping, we don't map a land cover of year 2020. We map a land cover of last 20 years. Or maybe we can map 30 years. But so we switch from doing spatial modeling to space-time. But when you look at the space-time data, it's not just like if you have a space, you have a 2D. When you look at the space-time data, it's not that you just add a third dimension. So you go 2D, 3D, but you have a 2D plus time, and it's a special dimension. And so what's special about it? Number one is, for example, in a spatial dimension, XY dimension, if you look at left and right, then the left can impact right and right can impact left. Yeah, it can be connected. There can be a, let's say, the diffusion movement in the space. But when you look at the time, the future cannot impact past, right? So you have the causality, it's only one direction. Then also with the time data, I will show you there's all the field, there's a whole field of statistics, which is called time series analysis, which looks at the behavior of variables through time. And it's way more complex than just changes of variables through space. So we are going to talk about that. Time dimension, it's easy to plot, remember that, but it's difficult to model, basically. That's the, and then what is especially very difficult is to predict the future. And that's what some people in time series analysis, when they blindly use the models, they say, okay, now I predict the future. But the prediction of future can be very poor. And so it's very difficult to, especially to predict future. You can predict inside the observed space and time. Like, so if we predict land cover for last 20 years, then we can do lots of testing. But if I have to predict a land cover for 2022, you understand? It's going to be very difficult because you need something on the level of magic really to do it. But you could, for some variables, you get very close. So you can actually predict future also. If the variables are kind of like the trend component, the systematic component, it's, let's say, it's proven to be like dominant, then you can also predict some models you can extrapolate in the future. So we're going to talk a bit about time series analysis, visualization of data, and I will point you to many books and references so you can, maybe some things are new, maybe some things you know. But I will point you. Any data that has a so-called spatiotemporal reference is a spatiotemporal data. So obviously you need the coordinates. And if you talk about geographical data, the coordinates are latitude and longitude. And then what is also very useful to know is the location accuracy. So that tells you about these XY coordinates, whether they relate to something, which is plus minus 100 meter, 500 meter, I don't know. But also there is the size of the block you sample. You could also do block sampling, and you have, for example, for soils that do block sampling. So they say this is the value that relates to a volume of a soil. It doesn't relate to a point. And then you have the height above surface, the elevation, because this is elevation as of terrain. But you can also have, for example, temperature, daily temperature. Is it the surface temperature? Is it at 2 meter or is it at 100 meter? So you can have a different vertical dimension, and that's this third dimension. And then we have the time. And time you represent actually with two columns. That's the beginning of the measurement and end of the measurement. I will show you that that's very important because time has also so-called temporal support. So some things we measure like daily values, monthly values, value at the second. So it's very important. And then you get the spatial temporal data. And once you know these coordinates of the data, once it's a spatial temporal reference, then you can import it and do spatial temporal modeling. So this is actually what I said. Time is just another spatial dimension. And there are specific methods that are developed for spacetime data. And when I started in R, when I was using R, I think in 2013, I think then, or 2012 already, Edzer and the colleagues, they made this spacetime package. And it was really a great solution because at that time there was only spatial data, SP. And then he says, okay, he looked at some problems in the data, and then he made this spacetime package. I don't know if you ever used it, but when you read some the tutorial, then it becomes a bit complex because there's this full spatial stack and irregular data stack. So he made these classes of data. So it's a quite complex to understand. It's a bit abstract, but in principle, the most important is that you have correctly for data, the spacetime reference, and then if you have that, then you can import it in R, organize as a spacetime class, and then we will show you with some data examples. You can plot the data, you can do spacetime overlay, you can do spacetime modeling. And this is this paper also from Edzer called Spacetime. It's published in the Journal of Statistical Software. Have you used Spacetime? Anybody use Spacetime? Completely new? It's also magical when you think about this. So the Spacetime data, imagine you can have a Spacetime time series of satellite images and you load them into R. And if you organize them, as you say, this is the class Spacetime regular data frame of as it called Spacetime full data stack. And then you prepare the point data, and this can be irregular. And then you say over the points versus the Spacetime time series, and it will do a Spacetime overlay. So it will match the points with the cells in the Spacetime. And so that's really magical because you then do it in one line. The problem is when you work with the large data, you cannot load it in R. Your RAM is not going to handle it. The R is not so, or let's say we are not so efficient with, putting things in RAM. So then you have to, maybe this Spacetime package wouldn't work. And I don't use it, by the way, because we work now exclusively with large data sets. So I will show you, we're going to use the Terra extract, which will do then the Spacetime overlay. But my code, unfortunately, maybe not so easy because this Spacetime overlay, I will show you just very quickly how the code looks like. So it's a bit longer code. Don't get scared, and it runs in parallel. So this is the Spacetime overlay for meteorological data. We have a time series of MODIS land surface temperatures, and we'll do a Spacetime overlay. And so I made this code. It's not in a package yet, but I should put it in a package. And you see this code will run in parallel. So it runs in parallel. And I made a little function called extract ST, extract Spacetime. And this thing is a universal function. So this function, if you use this code with your data, it will, I promise, it's the fastest way you can overlay a large amount of points over large stacks of geotiffs. And they don't even have to be stacked to exactly the same grid. They can be loose structures. So that's the space-time overlay. And then when you do after the overlay, you will get this so-called space-time regression matrix, and then you can do modeling. So I'm going to do this code today. I'm going to show you how it works, and we're going to go step by step. And then I will show you the data structure, what comes out. I will also show you when I do computing, how it goes into parallel. So we will look at it, observe it here when it goes to parallel, and so that you get the feeling that you understand what's behind. But again, I build up the thing that I showed you. I build it up on top of the package made by Robert Hymas, which is called Terra package. And this one allows, so that's this extract STUC. This is the function that allows to do very quick overlay. And it's actually magically fast. We overlaid millions of points over like, I don't know, 1 terabyte of data, and it will take 2 minutes. So it's a magically fast. And this is mainly because the Terra is a program mainly in C++. It's another language that is something you should consider, but C++ is a different story. Okay, going back to the slides. So there is also a new book called Spatial Data Science. Have you heard of this book? And this is the URL. URL is very cryptical, Kim Schwartz 3146C4. It's a very cryptical URL. Don't ask me, but Edzer is the main author. And they are writing that you can subscribe to it and you will get a notification. So every time they write a new thing and the things they discuss, you can follow it. So it's a live book. Basically, they write the book and you can follow them. You can see all the mistakes they do and the fixes. So they write book in front of everyone. So it's a new age writing of science. I think it's the right way, by the way. It is a book down based, so it's you can see all the code. Everything which you see, it's in a code. And you see there's a chapter 13, multivariate and spatiotemporal data. I don't know how much they have, but they have, I think, only spatiotemporal geostatistics. So if you go to this book, which will be cutting edge, you will not find anything basically that we are going to teach you. Very little. So everything we teach you, it's not in the book because we do the machine learning for space-time. So I think we have a lot of original things for you. But maybe they will add it, I don't know, because as I said, it's open book. Maybe at one point they will say, okay, we add one chapter on space-time machine learning for mapping. Okay, this is just to show you the space-time reference. If you use Google Earth or any type of data in KML, keyhole markup language, then you can see how it looks like a space-time reference. So you see here I have a name. This is a station that we use in the first exercise. And we see that there's a measurement at some point, and point has the coordinates, and it has a begin-end time. And you see that's all these theoretical concepts I tell you, they are implemented in many software. So for me, actually, as I said, for me now, mainstream is to do space-time modeling, space-time analysis. And for me, any GIS where I cannot set up a space-time, for me, it's a cumbersome. We cannot do our work. So we have to use only the GIS where we can do space-time. And so one of the most popular GIS is the QGIS. Does it support space-time? Does it support space-time? Do you know? Pablo, you don't think so?
I don't know.
There is a plugin. There is a plugin to go around it, but it's not. If you just start the QGIS and you say, here I have a time series, you know, you're not going to get a slider, right? That's one of the reasons why we develop original interface, because you see all of our data, it has a slider. There's only a few data sets, there's no slider. But 95% of data, there's slider. So as soon as you start the data, there is a slider, right? And so when you go to QGIS, if I open some project, You know, you say, well, I have this temperature data. I want to slide through time. You won't get it, but there is a plugin. There's a plugin for time series data, and this it's not going to animate changes. You have to play with the animation. But if you move around with the mouse, you will get the curves. You will see the curves of the values. And that's also amazing. Somebody made this plugin. What's the name of the plugin? Do you remember, Carmelo? No, another value for the time series. I have to also remind myself, but there is a plugin which allows to time series Explorer. There's a couple of plugins, but I have to actually remember which one is the one that Leandro uses upstairs. Maybe please check with Leandro. So, but there is a plugin, and there's more plugins, of course, as I said. But there is a plugin to put it, and then you can see how the values change. If you have a time series of values, how does it change through time? At the moment, if I want to see changes through time, I have to do this. I have to click on and off. That's the only way. That's the QGIS. People that are experts in QGIS, if they watch this video, they will say, no, you're doing it the wrong way. You should do like this. But officially, it's not easy to just go, hey, here's the space-time data. I want to see changes. It's not easy in QGIS, but it's possible to set up. So when you have a moving object, and if you maybe follow me now, I might sketch it on the screen there. So when you have like something like a bird, right? Bird is very complex. Maybe car is better. When you say car, then the car moves to some streets, right? And goes somewhere here. Goes from location A to B. But and when you plot it in let's say some web map up, you know, it's just a point moving. But you could also plot it as a trajectory. So you plot that line of movement. And you can plot the trajectory in space-time. So you can make a space-time cube, something like this. So that will be x, y. And then this is the time, and time goes this way. So if you plot it, then you have something like trajectory moving up in time. Have you ever seen this? So I was doing that for 2 years when I was in Amsterdam. I was plotting these trajectories of bird movement. And it's very funny because you can then in this space-time cube, you can see how this overlaps between species through time, which you wouldn't be able to see if you just had a 2D view. So you can see the density. You can rotate the cube, and you can see the density where they overlap in the movement, right? And so this is also another way to look at that. And so now you have this. So you have objects, and objects have trajectories. And then you have also fields. And so what are the fields or regions? So I wrote here what could be the fields or regions. The next slide. Basically, it can be one of the three things. It can be a quantity or density of material. So it's not a physical entity. So that's like molecules, you know, quantity of molecules. Let's say, you know, some element in soil. Or if you think about pH of soil, this is quantity of elements. And so these are, or density. Then it can be energy flux. Energy flux, because energy also moves, like if you look at the heat, it moves through space, right? It's not a physical entity. It's a movement of energy. So you can also model that. And then this is where it gets a bit confusing. You can also do modeling probability of occurrence. And so this bird movement, I could also represent it with probability of occurrence, and then represent it as a region. Okay? But actually, in the original sense, it's entities, it's physical entities. But I could also model them as regions. And when you look at this map I showed you basically on the Open Data Science viewer, this one, it's basically an urban fabric. It's a physical entities, and most of land cover, it's physical entities, but we modeled that as a probability of occurrence. So if you say, theoretically speaking, how could we model this? Well, we could model every house as a unique entity. You understand? If you want the total land cover, GIS, then I will model every tree, every house, everything which is a physical entity. I will model it as a physical entity. And this is maybe in about 10 years, this is how the land cover maps will look like. Because maybe in 10 years, in Netherlands already they inventory all the trees, I think. Did you know that if you're not from Netherlands? They have a data set you can access. They map the whole country 1 to 1,000 now, I think. And they mapped basically every tree. And next thing, they will chip every tree. Yeah, so they know how the tree is doing. And there's already a concept called tree talker. Have you heard of it? So they put a chip on a tree and they follow the health of the tree. Every 10 minutes, you get an automated sensor network. And so that will be a land cover in the future, that you wouldn't map the probabilities, but you will take any object that you consider as a land cover, land use, and then you will track it through time. And so when you come to GIS like this, maybe if I'm still working in maybe 15 years, we go, here's the Netherlands, and here are all the homes that disappeared and the new homes built and right? That's how the land cover maps will look like. So, but this is just talking about concepts. First, distinguish that there are models, space-time models of objects, of physical entities, and there's models of quantities. And quantities can be densities or masses or volumes, or it can be energy fluxes, or it can be a probability of occurrence. This is the Spacetime Cube. This data set you see here, this is this data set we're going to use here, which is this meteorological stations for Croatia. And you will see that when we make on the end, we will make predictions, and predictions will look something like this. Now I have to actually show you that because I don't have it computed, but I have to show you here. So we will make these predictions and they will look something like this. So you will see we will do space-time interpolation of daily temperatures, and we will predict for every day, we will predict how the daily temperature changes. And you see this is the stations and these are the predictions. So this is the same data set. This data set is shown in a Spacetime Cube. And here is shown on a 2D map. Yeah, it's not easy to match, right? You're like, well, no, it's not the same. But there are meteorological stations and you have the measurements every day. They have measurements. You see some stations, there are no measurements. So what happened here? How come there are no measurements? They had a day off on the meteorological service. No, so what we did when I started working with this data, so I said, hey, let's do space-time. So we say, hey, meteorological data is space-time. It's high quality, there's lots of data. So let's do meteorological data. And when we started working, if you look at it, they have something like 160 stations, and they may have measurements daily. Yes? So you have 365 days by 160 stations. That's a lot. When you load it in R, when I started doing, this is not going to work. It looks like it's only 160 points. But when you load all the space-time data, and if you take, let's say, 3 years, you're loading millions of values. And that's the difference between space-time and space. In space-time, you get overloaded with the data very quickly. So what I had to do, just to do this plot, just to make this plot, I had to subset to, I think, maybe 2%. This is what you see here is a 2% or something like this, because I couldn't plot it in R, and I needed it for the book and for the paper. So I said, oh, this is not going to work. Let me subset. So I just randomly took out some points. So you get an idea, but for the sake of plotting, I maybe plot here maybe 50,000 points. Sometimes when I say point, by the way, now imagine this, when I say a point, if you're in a space-time modeling, then you say, well, you're talking space-time points. You understand? Because the point, still in many GIS, when you say point, the point is, it's just this thing with the location, the station location. They say that's the point. But in a space-time modeling, the point is every measurement in time. So one station can have millions of points. Okay, so also be careful with that when you say, I have a problem with that point. Usually when you do space-time projects, then when you say I have a problem with that point, they said, I have problem with this coordinate and this time, this day. That's why I have the problem. Okay, but there's no problem just with the station coordinates. Okay, so this is this thing, and back in 2012, when I started going like, okay, let's work with space-time, and this thing we call 2D plus time. So you have 2 dimension and you have the time. We don't model changes above surface, below, whatever. We didn't model that. So we did this 2D plus time. And at that time, I work a lot with technique in geostatistics. I work with geostatistics. And one of the techniques I work a lot with, it's called regression kriging or universal kriging. And then I said, let's do this. Let's apply universal kriging to space-time data. And we managed to publish this paper. And you see there's quite smooth predictions. So we published that data set and predictions, but we did it using universal kriging. It means we only use basically linear statistics. And what we're going to do here is the basically same thing we do with spatiotemporal interpolation, but using ensemble machine learning. So we don't use kriging, etc. We use ensemble machine learning to do space-time interpolation. Okay, and you will see it's a bit more computational. When I say a bit more computational, it's about 10,000 times more computational. But the effect that you can gain is that you can possibly increase the mapping accuracy. And that's why we, of course, use it. That's the magic. If you get the machine learning to better represent some nonlinear phenomena and to better subset and optimize, fine-tune parameters, then you are motivated to switch to machine learning. That's usually why people switch to machine learning. And we're going to talk about that also in the second block today and in the third block. This is what I said, what we did 2012. Fast forward 2020. So last year, we started doing this. We prepared a 10 terabyte cloud optimized GeoTIFF, a Landsat time series. We gap fill it. We removed all the artifacts. We prepared it. It's a 10 terabyte data set. Then we do SpaceTime Overlay. SpaceTime Overlay takes about 4 hours. So, Carmelo, do you remember for the land cover or longer? How long will it take? No, to overlay, just the overlay. One day, so like 20 hours or something. So it takes 20 hours to overlay 7 million points over 10 terabytes of data. Okay, you would think, wow, it's a 1 day. Try to do it with any other method. If you get it faster, we will be very, very much like to hear from it. This is the fastest we could get it. Imagine the fastest we could get is a 1 day to overlay. And then, so basically 1 day is you leave it also overnight, and we run it in parallel, right? We run it in parallel, and you can parallelize maybe further, but eventually it takes a long time. So we did a space-time overlay, and we add also some other covariates, and then we fit the model. We do space-time overlay, fit a space-time machine learning, and we made these predictions. And this is what you see here. This is the predictions. And you know, there's people criticize. There's some homes, you know, they appear and disappear. So we have some places where you have a home 1 year, and then next year there's no home. They say it's impossible, right? So there is absolutely there's noise, but we did some time series analysis to that, and when you smooth out the noise, we get accuracy on the second level and third level. It comes to 80%. So it is comparable if you look at the Corine, let's say land cover. This is now the state-of-the-art European data set. So this is Corine, and this is what we did. And they have also SpaceTime. There's also SpaceTime, so you can scroll, but it's every, I think, every 5 years. And also the polygons are quite large. And when you look at our data, we have it every year, and we have 30-meter resolution. So much higher resolution. And we can update. We don't need, you know, every time they do new coordinate, they start from scratch, not from scratch, but they have to, you know, get all the data and And we only fit a single model. Imagine a single model to model land cover. It's mind blowing. We had a single model, and now for the 2022, we don't need any point data. We don't need it. We only need the satellite images and the nightlight images. That's it, and we make the prediction of land cover. And so that's also one of the reasons to use the SpaceTime. And so you can play with all these things. It's super cool, super important to have this functionality to do this swiping, and so you can see the differences in different data sets. And we will keep on adding data sets. And also, if you do a European project, if you produce a pan-European data set that matches the specifications we use, we are most happy to host it. So we're hosting it on us, so we're most happy to host it. Let me go further. This is this results of predictions. This is just a one tile. When we do predictions, we split the whole Europe in tiles. I think it's 8,000 tiles. We use the 30 by 30 kilometer tiles. And then we do predictions, and you can see this is a one tile in Sweden, and you can see the changes. At the start of the project, I was thinking, oh my God, land cover changes 20 years Europe. Maybe you won't see so many changes. We were thinking, oh, maybe this is, it will be difficult to see changes. Then when we got the results, we were surprised, actually. Lots of Europe is very dynamic. First, you have urbanization happening. In Sweden, there's a lot of, I think, forest management is more dynamic than in Southern Europe. So we saw a lot of changes. And now we're actually very excited because we would like to go back. We will go not back to the future, we would like to go back to the past. And we would like to map it up to 1990s so that you can even see what was the history of Europe land cover-wise and environmental data-wise, going from 1990, even 1985 if possible, up to today. All these things I'm telling you, by the way, there is a paper and you can read it. It's not, it's still in review, so it's not accepted yet. So use it with a grain of salt, but more or less it's all described here and you can read. And if you want to cite this, you can already cite. So one thing worth learning is that, and noting, is that when you have a 2D data, you know, if you do geostatistics, you have a variable of 3 parameters, and you have NS locations. NS is for like station or space. When you have the 3D data, you have a depth, then you have 4. When you do 2D plus time, then you have many more measurements. They go exponentially up. And if you do 3D plus time, then it's mind-blowing. Then you have not only changes through time, but also through vertical dimension. And then you have literally can have like a billions of observations. And there is in our tutorial, there is a one data set. Also super happy we published that paper. It's called Cook Farm dataset. And this is a 4-dimensional GIS. So you have measurements with the automated sensor network where the sensors are in different depth in soil. And you can do predictions also in 4D. And so I will show you also that here we use this altitude. So we use a depth also as a covariate. And then we model machine learning changes using the depth. And here I show you only one prediction. I think I make a one prediction because it's over a depth of 30 centimeters. Right? But I could make predictions through space-time for the different times and for different depths. Now, how do you visualize that statically? How do you visualize the 4D when you have when you can only do it in a paper? How do you do it? Well, it's not too bad. Let me show you how we did it. We did this. So I downloaded all these papers locally, so I don't have to look online. So here's the papers, and this is the 2015 paper. And so how do you visualize the predictions in 4D? You have to make something like this, this one. So you have this is the time, it's this direction, and then this is the depth. And believe it or not, you can visualize it as GIS, the 4D data. You can visualize in GIS. In which GIS you can visualize 4D data? Which is the GIS that supports 4D data? Do you know? It's Google Earth. In Google Earth, you can visualize 4D data. And I will talk about this in the second block. And also tomorrow, I have a session on Google Earth. So please come to Google Earth. I will show you that you can actually put these slices and you can visualize them through time. So you can see how variable changes through depth and through time. It's possible. But then you have to move to Google Earth, to KML basically. But it's possible to visualize 4D data. I don't know about QGIS. Time series. This is a time series example from Wikipedia. I think this is just some noise with a trend. Yes, but so they use it to visualize. This is like time series. Time series data can look something like this. It can be very noisy. When you do time dimension, then you have to consider. I have to understand time series analysis. Time series analysis is a lot of things. I don't have time to talk about all these things. So what I just give you a really super short, like a 1 minute run through time series. So number one about time series is that lots of analysis is focused on so-called decomposition. Decomposition, if you look, this is the original signal. It's obvious when you look at it. So you see there's some trend component, and there's some seasonality component. They can be split. You split them, then you say this is the trend, this is seasonality, and then you have like a random component. And that's many time series does this decomposition. And then also how you fit this trend, which smoothing you use. How do you separate from what is a noise, what is seasonality, and what is trend? And that's the whole science of time series analysis. One example of the time series data is the coronavirus in the Netherlands. These are the infections. There is a corona dashboard for Netherlands. And so you can go here in this dashboard. It's in Dutch, of course, but it's very well done. I don't know if your country has it, but at any stage, it's kind of like in sports. You can follow the scores and tables, and so, but it's a dark humor, of course. It's a serious thing. So you can follow the people getting into hospitals, number of vaccinations, and these are the positive tests. So we can go. It is also GIS. GIS very important. So I can go and find. This is Ede. We are here, Ede Wageningen. So we have 10 positives on 100,000. So that would be about 4. It's about 4. So 4. Yesterday, I don't know, 4 people had they were coronavirus positive, and then you can follow. Unfortunately, they had also a time slider, so you can go through the time. You can slide through the time and see where in space there was more. Now it's very chaotic. It's really like leopard skin, so it's very chaotic. You used to be big cities; they used to be the hotspots. Which you will expect, but now even Amsterdam has less infections than some little area in Friesland. I don't know, but this one is a time series, and this plot is of course wrong because it looks like the last year March there was less infections. So this plot is wrong. By the way, it's bias plot. Yeah, and why do they give a bias plot? That's another question. I wouldn't have done it. I would have normalized it so it gives the correct picture. But imagine the correct picture will be here is a peak. Here's a peak that goes down because then there was no testing. The testing just started, I don't know, in April or something. Then when they started testing, then it went down because there was a lockdown. And then there was we had the summer school here. Summer school, when we had the summer school, they started going up, but still less than now. And now it's in and now this was the vaccination starting somewhere here. from April, vaccination starting, and then the numbers dropping, and this was the delta. Delta came from, I don't want to put geographical locations, but in Netherlands, most likely via England, the delta came, and delta was a big problem, but not so scary when you go back to the hospital. People having really problems, they had to go to hospital. Then you see that delta was not as a big problem as in October last year. So it's about even like 7-8 times less. So it means the virus is less deadly for us, basically. But you see, this is the correct picture because this is in April last year. So there was probably much more infections, but there was no testing. So they never normalized the data. So that plot is actually, it's a bias plot. It doesn't show you the real picture of what you're interested in. And so you see this was the peak. So Netherlands never went back to that peak from the last year. So we went to some little peaks here and here. So you can say there were three, let's say, three distinct peaks. And then this was like a fourth milder, and this one, this is delta here, but less deadly. So that's, let's say, some good news in a way. Reason why we're doing this workshop is that we knew that it's a less deadly, like way less, 5 times less deadly. So otherwise we would have done everything virtual. But we said, look, it's getting people get vaccinated. Congratulations to Netherlands. Netherlands is, I think, in the 5 most vaccinated countries in percent, fully vaccinated. They're top 5 in the world. From the bigger countries than 1 million, I think there's Canada, Netherlands, Israel. So a couple of countries, they have really high vaccination rates. And I think, as far as I know, 90% of people do want to get vaccinated in Netherlands. There's only 10% don't want to get vaccinated. Okay. So you see, this is the time series, and you have these components, and you have the trend component. So what is this trend component? So we will take a look at that, and what is seasonality. So let's look at the temperature. Let's say, doesn't matter if it's surface above 2 meters, but the world temperature. If you look, this world temperature have these components from time series data. And one interesting component is the long-term oscillations of the temperature. And they are connected also with ice ages. So this here was the ice age. Yes, so this is the ice age. Then the ice age finished about 9,000 years ago. And then you have the global mean temperature going up. But it's a gentle change. It's a, going from minus 0.3 to plus 0.3. So it's a change of 0.6 degrees. And this is how normally the temperature of the planet goes through this interglacial periods, goes up and down. And there are some oscillations also here. If you want to read about this glaciation and why does the global temperature changes, it's very complex, actually, it's the whole field of physics. But what you have to know is just there is a distinct long-term trend and the temperatures change. And this is industrial revolution going 150 years ago. And now in this plot, that's why the industrial revolution is scary and global warming is scary, because in this plot, you see this red line, this is what happened now with temperature. We are going to rise the temperature 1.5 degrees. It goes beyond this plot. It goes beyond, this is a bit older plot, it's only up to year 2000. But we completely disrupted this long-term trend in the global temperature. And then when you zoom into years and days, then you can see the temperature and also here water content. Temperature is much more regular. This is actual data, and then we just fit a spline. This is the Cook Farm data set. And we fit a spline for different depths. And super interesting, when you look at the soil is like a buffer for temperature. So you see on the surface, you have higher and lower oscillations. And as you go deeper in the soil, the temperature stabilizes, oscillates more. And soil moisture, other way around, you have actually more smoother oscillations on surface and then more oscillation in the deeper soil, because the water goes through the soil. It doesn't stay usually on the surface, but it goes through the soil and then accumulates somewhere. So when it accumulates, it becomes more stable. And you see there's this seasonality effect. And this is something that seasonality can happen. There's a daytime seasonality, so you have a day and night oscillations in temperature, and you have the seasonal oscillations. So that's like winter, summer, etc. So the temperature actually has two cycles. It has the oscillations inside the day and oscillations inside the year, and they're both very systematic, right? There's always nights are cooler than the day, summers are warmer than the winters, etc. So it's always very systematic. Okay, so that's the spatial temporal data. How do you visualize spatial temporal data? So you can do static plots. So some of the plots I showed you, this will be a static plot, and you can visualize four-dimensional data. It's possible. And is this objects or is this regions? Am I plotting here objects or regions? Somebody? So obviously there's no, like, I don't use any vector structure, and we're talking about water content, right? And water content, what did you say? It's kind of a density. So it's definitely a field. You represent it as a field. So I present it with the gridded data. Yeah, so I just show what is the percent of the water in soil going from 0.15, so 15% to 60%. So there are some pixels that potentially get to 60% water, depending on the period. So that's a static visualization. And then I can do time slices. Time slices is doing something like here in the QGIS. These are the time slices. When I do this, you see, these are 2 days. This is 2006, August 15, and this is 2006, August 18. So when I produce time slices, if I do this, I visualize space-time. Yes, so this is visualization using slices. So that's another way to visualize. And then the other thing we can do animation or interactive plots. And animation interactive plots, this is this thing here that you go and you create animation, and you can choose your speed. You can slow down or do it faster. Yes, but you can visualize space-time data. And so these are the main ways, as far as I know, that you can visualize space-time data. The most simple way actually is to have like just one static image, and then put a point to that time series data, and then just show something like this. Then you just show the cross through that moment for that spatial entity. That's the most simple way to visualize. Then you simplify the data from 2D plus time. You simplify it into the time only, and you just have then the time series data. This is kind of the most simple way to visualize. And this is when you go in the data portal here. And if I, for example, click somewhere here, I don't know, then as you see, then I get this thing. And this is the most easy way to visualize space-time data, just having one static image and then having a time series of the values for that specific query point. Okay, and then you also visualize space-time data, but we only know about that point. Now, here's a nice example. This is the package I made years ago, but I'm very sorry I don't maintain it so well, so I'm not sure if it runs still smooth. What I can do, I can put this data here, load the package. This is called a foot and mouth disease data. And as you see, I can load the data. It's in a package already. And I can pick up the points, pick up the dates, and I add to the dates, I add a new column, which is the reported day of disease. So foot and mouth is, that's somewhere in UK, where they observed location and time when some cow got the disease, okay? And so that's a space-time data set. And you see, I can put the data into the spatiotemporal irregular data frame. STIDF, this is from the space-time package. So I start with having just the data set looks like this. Let me see. So I have something like this, or it's already converted. Let me see, I have to do like this better. So I have it as a simple spatial object first. So this is just a spatial points data frame. So I have the 648 observations, and I have the reported day, but it's just a spatial object. It's just so you see the sum of the coordinates. If it was not irregular, if it was a regular, then it would have been repetition in coordinates. But because an irregular, every space-time point has a new coordinate, and then I convert that into the space-time data frame, and then this one looks like this. So now it's a space-time object. And it's a bit more complex structure because it has the data, the values, then it has this locations, and it has the time. You see, and even has some time index, etc. Okay, so it's a higher complexity object. In this case, it's a high complexity object, but it's the most simple extension, and it's called space-time irregular data frame. It's a more simple extension because basically it's just a 2D plus time point data set, where time is not kept as a location in the SP part, but the time is kept in a separate slot, which is the time slot. And if you do it like that, when you come to this example, if you use the plot.kml package, you can go and make that plot. You do plot.kml, and then we create it. We create a KML file that I can open in Google Earth, and we can now look at it. If the Google Earth starts. No, maybe I'll have to restart it. But we can look at that data, how the values change through space-time. Let's see. How do I kill the Google Earth? No, I think I have to check with the lander how was the installation made for Google Earth. I could try to pass this data I made. Let me just see if I can do it. Code. Because here I made that data set, and I think I can pass it to this Windows 10. And it should be visible from my Windows. Yes, let's see if I can open in Windows. And I will check in the break what's up with the Google Earth under Ubuntu. So here now we're looking at this data set, foot and mouth disease. And here's the data. I plotted it with plot.kml on purpose. I put going from blue color to red color. Blue color is the early cases, red color is the most recent cases. Have to remove all these other things. And so here's a space-time data set. And imagine now we can visualize it. The guys who make Google Earth engine, they understand statistics. So you see they have this temporal support. So I can play with the temporal support. And I can scroll through going up or forward, and it will go very fast. So why do I use this visualization? Well, it's a complex thing, this foot and mouth disease. And what do you see from that foot and mouth disease? This is so at the beginning there were a couple of let's say outbreaks. So there will be only like 3 outbreaks. Then they started spreading. They're spreading all around, and then they spread also further down here. And then again, there will be just a one, because here they stopped, here more or less they stopped. At the beginning, it was very fast, then it stopped, and then kind of a second outbreak here. But you see, interesting, like this outbreak here, it happened, but then nothing happened serious. But when I look at here, then it got again bad. And that's the way you can visualize space-time data. Is this are these regions, or are there objects? Come on, guys, wake up. This is obvious from the image. Well, how do I use to represent it? What do I use to represent? I use like a vector structure. So obviously these are the actual cows that are observed as getting sick. And so these are kind of objects. But I could now, what could I do to create that, to convert it into grids? What could I do? Well, I could calculate the density. I could, for every, let's say, a week, because this goes a couple of weeks. I mean, it's over from March to August, September. I could take every week and I will calculate the density of cases, like a kernel density. And then I have a time series. Yes. So anyway, but it's a nice thing to be able to go from R directly to Google Earth. Yeah, and you can play with that, and that's something I will talk tomorrow. I will show you the plotKML, and you can easily change the way you use the color. You put another color scale, and you can add also elevation. I don't know. So you can play with this, what we call space-time aesthetics, and then you can create your own visualizations. So that's the other very nice thing is the Google time lapse. So if we look at the Google time lapse, have you looked at the Google time lapse? You can pick up any location in the world. And this one is the Wageningen. And you can see last 40 years, you can see this Landsat images, last 40 years. It plays animation. So I cannot zoom in more because the resolution is limited. But you can see how the Wageningen changed going back all the way back from the 1980s. So it starts from 1985, and you can see that. You can see also Landsat getting better. You can see campus growing, you know. So you can see campus growing. Campus used to be very small, of course. 1980s was like 2 buildings, I don't know, nothing, but with just the cows there, I think, just a farm. And now it's a big campus. So you can play that video for any location in the world. And there's also, of course, the Google pick up the ones that are most interesting. So that will be some really construction sites or somewhere in I don't know, in a tropical forest disappearance and things. But please play with it. I don't have time for that now, so I will turn it off. But please play with that Google time lapse. It's a history of the planet, except it's just history through images. There is excellent book on space-time data by Oscar Perpignan. He was also in our summer school 1 year, but he has all these workout examples and there's tutorials. So please take a look at that if you're interested. The book is just behind the link, and lots of things it's available just in the code, so you can reproduce it with your own data. You can also make animations and things. So if you never heard of it, it's a fantastic book, slightly outdated now. There's a lot of new developments. There's the TMAP package, which you can watch the tutorial from our summer school last week, tutorial by Martin Tenekes, and also excellent package. And there's also animation in the tutorial. So if I if I will go back, then you can see. Then you can see these animations. And there is also a book called Geocomputation with R. Also fantastic book by Robin Lovelace and Jakub and Janes. So also fantastic book. And you can also read about how do you visualize space-time using, for example, in your book, you know. So you can have a book You can make with the R, you can make a book, online book or tutorial, which will have animations so you visualize things with animation. So you don't have like a classical book with a static image, but you scroll through images and you will see actually animations of things. So that's somewhere checked animated maps. You see, so I'm looking at the book. It's really magical that one picture in a book, it's actually animation, right? So it's not an interactive animation. There will be books soon that you have an interactive space-time animation, so you can play with the things, like the things I showed you here. Imagine if I had inside a book that you can go and play directly with the Google Earth or something. So that will be also awesome. But you will soon have books that will have that through leaflet or through some other way that you will be able to play in a book with the space-time data. And with this thing, I think I'm done with everything, just the conclusions. So what's important, what I said today? Well, you maybe know more than me what's important, but if I can emphasize myself, what's very important to understand that the extending from space to time is not trivial. There's a lot of things you have to teach yourself, especially the time series analysis. Then the second thing, prepare for the large data, jumping from space to space-time. It can be from 10 times to 10,000 times more data. And then if you want to do space-time, don't forget, you cannot force any data to space-time analysis. If you miss, for example, time for some locations, with many data sets, we have to drop the data because so unfortunately, surveyors didn't record the date when they went on the field. And many points we have to drop from the space-time data. Sometimes when you drop so many data from space-time analysis, let's say if you drop 80%, then you're slippery slope because you're trying on force to do some analysis with the data which is not fit for that analysis. So that's something you should also think about. And then to analyze the data, you can use geostatistics, and I showed you I did that with the space-time kriging. You can do process-based modeling, or you can do hybrid methods, and you can do machine learning, right? And we're going to focus this course, we're going to focus on number 2, the machine learning. So we're not going to talk about process-based modeling, and we're not going to talk about geostatistics. But my interest next thing is to do hybrid methods, so to combine machine learning with process-based modeling. But that's another extra layer of complexity. There are some groups that are doing it, by the way, experimentally, but that will be another, let's say, paradigm in spatial temporal data science. And with this thing, I close the first session. I will stop the live broadcast.